January 5, 1943. The waters off Guadalcanal, Solomon Islands. Commander Tamesuke Fujita crouched in the cramped cockpit of his Aichi D-3A dive bomber as American anti-aircraft fire filled the tropical sky around his formation. He had survived 18 months of carrier operations, witnessed the destruction of 4 Japanese flat tops at Midway, and endured countless American bombardments. Nothing had prepared him for what happened next. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. His wingman's aircraft simply disintegrated, not from a direct hit, which he would have seen, but from a shell that exploded 30 feet away, showering the Val with a lethal cone of shrapnel that seemed to seek it out with supernatural precision. The bomber erupted in flames without warning, without the characteristic near-miss splash or tracer trail that normally preceded such destruction. Fujita pulled hard on his stick, diving away from what he assumed was extraordinarily lucky American gunfire from the cruiser Helena far below. He was wrong. What Fujita had witnessed was not luck but technology that would fundamentally alter Japanese understanding of American industrial capability. The shell that destroyed his wingman contained a miniature radio transmitter no larger than a wine bottle, fitted with glass vacuum tubes that had somehow survived being fired from a gun at forces that should have pulverized them into dust. Japanese engineers, working with similar concepts since the mid-1930s, had concluded that such a device was theoretically impossible to manufacture at scale. The Americans had not only built it but were producing them by the tens of thousands. This single demonstration would cascade through Japanese naval aviation like a slow-acting poison, gradually eroding the confidence of pilots who realized they were facing an enemy with capabilities beyond anything their leadership had imagined possible. The story of how Japanese naval officers came to witness and fear the proximity fuse began not in the tropical waters of the South Pacific, but in the calculation chambers and strategy rooms of the Imperial Japanese Navy, where in the years before Pearl Harbor, a generation of admirals had built their war plans on fundamental assumptions about American will, American production capacity, and American technical sophistication. Every one of those assumptions would prove catastrophically wrong. December 7th, 1941, Pearl Harbor, Oahu. As Japanese aircraft tore through the morning sky, American gun crews fought back with everything they had. 5-inch naval guns thundered from damaged ships, hurling shells skyward at attacking dive bombers and torpedo planes. Each shell required manual fuse setting, a sailor turning a wrench against a clockwork mechanism while enemy aircraft dove through defensive fire. Most shells exploded harmlessly in empty sky, their preset timers detonating them seconds too early or too late. Some never exploded at all. Others fell back to earth, their contact fuses still armed. In Honolulu, 9 miles from the harbor, shells weighing 55 pounds crashed through roofs, detonated in streets, tore through buildings. The Hirosaki family died when a 5-inch shell flew through their restaurant window during breakfast service. By the time smoke cleared over Pearl Harbor, 68 civilians lay dead. 32 of them had been killed not by Japanese bombs, but by improperly fuzzed American anti-aircraft shells landing in the city. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The tragedy illustrated with brutal clarity what Japanese naval planners already understood. American anti-aircraft defenses in 1941 were primitive, relying on technologies that had changed little since the First World War. The mathematics were simple and unforgiving. Traditional anti-aircraft fire required 3 pieces of perfect information executed in sequence under combat conditions. First, optical rangefinders had to calculate exact distance to a target moving at 300 miles per hour, potentially through smoke, clouds, or tropical sun glare. Second, height-finding equipment had to estimate altitude against fast-moving targets that could climb or dive at will. Third, fire control computers had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach altitude. A sailor then manually set a clockwork time fuse. The shell was loaded, the gun fired, and the fuse mechanism counted down. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly, the shell would explode near the target. The odds of destroying an aircraft were approximately 1 in 2,500 rounds, fired under ideal conditions. In combat with multiple targets maneuvering through defensive fire, the odds dropped catastrophically. Admiral Isoroku Yamamoto understood these statistics intimately. Born in 1884 in Nagaoka, educated at the Imperial Japanese Naval Academy and Harvard University, Yamamoto had served as a naval attaché in Washington during the 1920s. He had witnessed American industrial capacity firsthand, toured the automobile factories of Detroit, observed the sprawling steel mills of Pittsburgh. Unlike many of his colleagues in the Naval General Staff, Yamamoto harbored no illusions about American productive capability. He knew that in a protracted war, Japan's industrial base, dependent on imported raw materials and lacking the infrastructure for mass production, would be overwhelmed. But Yamamoto had also observed American military readiness in 1941. He had studied the reports from Japanese naval intelligence officers stationed in California. He knew that the American military, despite its massive potential, was unprepared for modern warfare. The Pacific Fleet lacked adequate fighter cover. American torpedoes were defective, running deep and failing to explode. Anti-aircraft defenses were woefully inadequate. Army Air Corps pilots trained on obsolete equipment. The United States Navy had only 7 fleet carriers, and most were assigned to the Atlantic. Yamamoto's strategy rested on a calculated gamble: strike hard, strike first, destroy American carrier strength before the industrial machine could mobilize. Win decisive victories in the first 6 months while America remained unprepared. Force a negotiated peace before American production reached full capacity. It was not a plan born of confidence, but of desperate necessity. Yamamoto famously told Prime Minister Konoe that he could run wild for 6 months to a year, but had no confidence beyond that time frame. The plan required Japanese technical superiority in the opening phase of the war. The Mitsubishi A6M-0 fighter possessed superior range, maneuverability, and climb rate compared to any American carrier fighter. Japanese naval aviators trained relentlessly, with carrier pilots averaging over 300 flight hours before operational deployment. Japanese torpedoes were the finest in the world, the Type 93 Long Lance capable of ranges and speeds that American designers considered impossible. Japanese optical equipment, manufactured by companies like Nippon Kogaku, rivaled German precision. Most critically for Yamamoto's calculations, Japanese naval aviation faced American anti-aircraft defenses that statistics suggested would be nearly ineffective. If American ships required 2,500 shells to down a single aircraft, and if Japanese strike packages could launch coordinated attacks with overwhelming numbers, then American defensive fire would be little more than harassing. Carriers might survive kamikaze attacks in later years, but in 1941 and 42, skilled Japanese naval aviators operating from fleet carriers could press attacks with confidence that most would survive to strike again. This calculation held through the first months of the war. At Pearl Harbor, Japanese aircraft losses were minimal, 29 aircraft out of 350 launched. At the Philippines, Japanese air power decimated American air forces with minimal cost. At the Java Sea, American and Dutch cruisers fell to Japanese torpedoes and bombs. At Ceylon, Japanese carrier aircraft savaged the Royal Navy's Eastern Fleet. The mathematics of aerial warfare seemed to confirm Japanese assumptions. American anti-aircraft fire was a nuisance, not a deterrent. Then came Midway, June 4th through 7th, 1942. 4 Japanese fleet carriers, Akagi, Kaga, Soryu, and Hiryu, were caught with aircraft on their decks during rearmament and destroyed by American dive bombers. The loss was catastrophic not merely for the carriers themselves, irreplaceable assets in Japan's limited industrial capacity, but for the 300 experienced pilots and aircrew who went down with them. These were not novices but veterans of Pearl Harbor, the Indian Ocean, and 6 months of continuous operations. Their experience could not be replaced. Yet even at Midway, the fundamental equation of anti-aircraft effectiveness remained unchanged. American ships fired thousands of shells at attacking Japanese aircraft. Some were shot down, but most losses came from American fighters or accidents. The mathematical relationship between shells fired and aircraft destroyed had not fundamentally shifted. Japanese naval aviators who survived Midway returned with damaged aircraft and casualties, but the defensive fire they faced was similar to what they had experienced throughout the campaign. American gunners were improving with experience, radar-directed fire control was becoming more common, but the basic technology remained the same. Clockwork fuses, manually set, detonating at predetermined times, effective enough to disrupt attacks, rarely effective enough to guarantee kills. By late 1942, the Pacific War had settled into a grinding campaign of attrition centered on the Solomon Islands. Japanese forces held Rabaul, a massive base complex on New Britain. American forces held Guadalcanal, barely. Between them stretched hundreds of miles of ocean where naval task forces clashed repeatedly, fighting for control of sea lanes that would determine whether Japanese garrisons could be reinforced or American positions supplied. In these night battles and daylight skirmers, Japanese naval aviation continued to take losses, but not at rates that suggested fundamental American technological superiority. Japanese reconnaissance aircraft reported that American cruisers and destroyers continued to fill the sky with anti-aircraft fire that looked impressive, but remained statistically ineffective. Experienced Japanese bomber pilots developed tactics to exploit American defensive weaknesses. Come in low and fast to reduce time for fire control calculations. Coordinate attacks from multiple directions to overwhelm tracking capabilities. Use the sun to blind optical rangefinders. Accept that some aircraft would be lost to lucky hits, but trust that most would get through. The reports from intelligence officers supported this assessment. American technology was improving incrementally. Radar was being integrated into fire control systems. New anti-aircraft guns with higher rates of fire were being deployed. Proximity fuses for anti-aircraft shells had been discussed in technical literature, but Japanese engineers familiar with such concepts knew the practical obstacles were insurmountable. Building a radio transmitter small enough to fit in a shell nose was theoretically possible. Making it survive 20,000 gravities of acceleration when fired was not. Manufacturing such devices by the thousands, maintaining quality control, ensuring reliability in tropical conditions, achieving acceptable cost per unit, these were fantasy notions that ignored the realities of mass production. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Japanese technical officers prepared detailed analyses for naval leadership. The fundamental equations governing anti-aircraft warfare had not changed in decades and would not change. Fire control could improve, gun crews could train more effectively, radar could provide better tracking data. But the technological ceiling was well understood. Without a proximity fuse, which all major powers had investigated and all had concluded was impractical, American anti-aircraft effectiveness would remain bounded by statistical probability. Fire enough shells, you might hit something, but the ratio of shells to kills would never shift dramatically enough to change the strategic calculus. What Japanese intelligence failed to detect, what Japanese technical experts never imagined, was that in laboratories and factories scattered across the United States, a different calculus was unfolding. The National Defense Research Committee, formed on June 27, 1940, had brought together leading American physicists and engineers under the direction of Vannevar Bush. Among them was Merle Tuve, a physicist whose work on radio wave propagation during the 1920s had laid theoretical groundwork for radar development. When tasked with developing a proximity fuse for artillery shells, Tuve understood immediately that success would require not merely solving technical problems, but reimagining what was possible in industrial manufacturing. The British had shared their research during the Tizard mission in September 1940. British scientists at the Telecommunications Research Establishment had developed proximity fuse prototypes that worked in rockets, which faced relatively mild acceleration compared to gun-fired shells. Their designs showed promise, but British industry, already stretched to breaking point, could not manufacture them in quantity. Cost per unit was astronomical. Reliability was perhaps 50% under ideal conditions. For military use, this was inadequate. British researchers passed their knowledge to American colleagues with the implicit understanding that if anyone could make this work at scale, American industry could. Tuvey's Section T at what became the Applied Physics Laboratory of Johns Hopkins University faced challenges that seemed designed to ensure failure. The fuse had to fit in the nose of a 5-inch artillery shell, leaving room for 7 pounds of high explosive. Inside this space, engineers had to fit a complete radio transmitter and receiver, a power source, safety mechanisms, and a detonator. All of this had to function in extreme temperatures and survive storage for months. Most daunting of all, it had to withstand the shock of being fired from a gun. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity. Every component experiences a crushing force equivalent to being hit by a sledgehammer. The shell then spins at 25,000 revolutions per minute as it passes through the rifled barrel. After surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942, faced the task of developing what the team called rugged vacuum tubes. Standard radio tubes of the era were 6 inches tall and weighed several ounces. They were designed to sit gently in radio cabinets, protected from shock and vibration. Van Allen needed tubes that could fit in a space smaller than a milk bottle and survive forces that would turn steel into powder. Working with Sylvania Company engineers, he redesigned vacuum tubes from first principles. Glass envelopes were thickened. Internal filaments and grids were shortened and reinforced. Tubes were potted in wax inside the fuse body to cushion shock. Through hundreds of test firings at the Naval Proving Ground in Dahlgren, Virginia, through thousands of design iterations, through failures that destroyed entire batches of carefully crafted prototypes, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during production ramp-up. They were right. By early 1943, reliability had climbed above 90%. But vacuum tubes were only one challenge. The fuse required a power source that could sit dormant for months, then activate instantly when fired. Standard batteries were too large and degraded in tropical heat. Engineers developed a wet cell battery activated by the shock of firing, with electrolyte in a glass ampule that would break from acceleration, flow over zinc and copper plates under centrifugal force from the shell's rotation, and provide electrical current within milliseconds. The design was ingenious, the manufacture was challenging, and quality control was critical. A single defective battery could render an entire fuse useless. The radio circuit itself presented another layer of complexity. The fuse needed to broadcast a continuous radio signal, detect reflected waves from nearby aircraft, measure the frequency shift caused by Doppler effect, and close an electrical circuit to detonate the shell when the target entered lethal range. All of this had to occur in a shell spinning at 25,000 revolutions per minute, moving at supersonic velocity, experiencing extreme vibrations. The electronic components had to be designed not just to survive, but to function under conditions that seemed designed to prevent any electronic operation whatsoever. By summer 1942, prototypes existed that worked under laboratory conditions. The question was whether they would work under combat conditions, and whether American industry could manufacture them in quantities sufficient to make a strategic difference. On August 12, 1942, the newly commissioned light cruiser Cleveland conducted live-fire tests in Chesapeake Bay. The targets were radio-controlled drone aircraft. Gunners brought down the first drone with just 10 rounds. They brought down a second drone equally quickly. A third drone was requested for further testing. Test coordinators responded that no more drones were available, because normally it took hundreds or thousands of shells to destroy one. The Navy cancelled the remainder of the test. Cleveland was ordered directly to the Pacific, with instructions that crew members were not to discuss what they had witnessed. Production was ramped up immediately. By November 1942, the first 5,000 proximity-fused shells were shipped to the Pacific Fleet. Distribution was limited to selected ships whose crews could be thoroughly briefed on security procedures. Under no circumstances were the new fuses to be used over land where unexploded shells might be recovered by Japanese forces. The technology was classified at a level comparable to the Manhattan Project. Loss of a single intact fuse to enemy hands could allow reverse engineering and compromise the entire advantage. Commander William Parsons, who would later arm the first atomic bomb aboard Enola Gay, personally escorted the first shipment to New Caledonia. He met with Admiral William Halsey to brief fleet commanders on the capabilities and security requirements of the new ammunition. The shells were distributed to carriers Enterprise and Saratoga and the cruiser Helena. Gun crews were trained not just in the technical operation of the fuses, which was identical to conventional shells, but in the absolute requirement for security. Any unusual anti-aircraft success was to be reported as improved fire control or lucky shooting. Under no circumstances were crews to acknowledge that their shells contained anything unusual. The date, January 5, 1943, was selected almost at random. Helena was operating with a cruiser task force off Guadalcanal. Japanese air attacks had been frequent but not overwhelming. American defensive doctrine called for maintaining constant readiness but conserving ammunition for actual threats. When 4 HED-3A Val dive bombers appeared on radar, approaching from the north, gun crews manned their stations and prepared for a routine engagement. The Vals had scored a hit on the New Zealand cruiser Achilles and were withdrawing at low altitude, a typical tactic to reduce exposure to anti-aircraft fire. Lieutenant Red Cochran, commanding Helena's aft 5-inch battery, had shells loaded with the new fuses. His orders were explicit: use them only against aircraft over open ocean. Do not waste them on uncertain targets. Confirm all procedures with fire control. The Vals were perfect targets. Low altitude, predictable course, over deep water miles from any land. Cochran's guns fired 3 salvos. The second salvo detonated near one of the Vals. The aircraft disintegrated, torn apart by shrapnel from a shell that exploded 30 feet away. For Cochran and his gun crew, the kill was satisfying but not extraordinary. They had been briefed on what the fuses could do. They had trained with confidence that the new technology would work. Seeing it function exactly as described validated their training but did not fundamentally surprise them. For the Japanese pilot who survived to return to base, for the intelligence officers who debriefed him, for the commanders who read the after-action reports, the incident was merely another data point in the grinding attrition of the Solomon Islands campaign. American anti-aircraft fire had scored another kill. Gun crews were improving. Radar direction was becoming more effective. The war continued. What none of the Japanese observers understood, what they had no framework to comprehend, was that the fundamental equation governing aerial warfare in the Pacific had just shifted. The mathematics that had governed every calculation of American defensive capability, every assumption about loss rates and operational tempo, every strategic plan built on the premise that Japanese air power could eventually wear down American will through sustained operations, all of those calculations were about to become obsolete. Not immediately, not dramatically, but with the inexorable certainty of a technological advantage that compounded with every mission, every attack, every engagement where American ships filled the sky with shells that found their targets with precision, that violated everything Japanese military doctrine said was possible. The transformation was gradual enough that individual incidents seemed explicable through conventional means. Throughout January and February 1943, Japanese naval aviation continued operations in the Solomons. Aircraft were lost, as they had been lost throughout the campaign. Pilots reported increasingly effective American anti-aircraft fire, which intelligence officers attributed to improved radar direction and better trained gun crews. Loss rates crept upward, from 5% per mission to 7%, then to 10%. Operational tempo slowed, as squadrons required more time between missions to replace losses and repair damaged aircraft. What Japanese commanders failed to recognize was the specific pattern of losses. Aircraft were being destroyed by near misses that should have been survivable. Shells that exploded 30, 40, sometimes 50 feet away were somehow generating lethal shrapnel patterns. Pilots who survived reported that American fire seemed to find them regardless of evasive maneuvers. The old tactics, coming in low and fast, using the sun, coordinating attacks from multiple directions, these methods that had worked for 18 months were becoming progressively less effective. The statistics told a story that no one in Japanese naval aviation wanted to acknowledge. In 1943, despite only 25% of American anti-aircraft shells being equipped with proximity fuses, those fuses accounted for more than 50% of Japanese aircraft shot down by naval gunfire. The proximity-fused shells were 3 to 4 times more effective than conventional time-fused ammunition. Night-kill ratios increased by 370%. The lethal fragment area of a proximity-fused shell was 3,000 square feet, compared to 60 square feet for conventional fuses. For Japanese aviators, these statistics manifested as a creeping sense that the rules had changed without warning. Lieutenant Takashi Morioka, flying Nakajima B-5N torpedo bombers from Rabaul, described the sensation in his diary. "We used to judge American anti-aircraft fire by watching the shell bursts, adjusting our approach to avoid the predicted zones. Now the shells seem to explode where we are, not where we were. The Americans have somehow learned to predict our maneuvers, or their shells have learned to seek us out. Either possibility is deeply unsettling." The unsettling sensation was compounded by the complete absence of explanation. Japanese technical officers examined debris from crashed aircraft, searching for evidence of new American weapons. They found standard 5-inch shell fragments. They documented damage patterns consistent with conventional high-explosive warheads. Nothing in the physical evidence suggested revolutionary technology. The shells were not guided. They contained no exotic explosives. They did not track aircraft. They simply exploded at precisely the right moment to inflict maximum damage. Admiral Takeo Kurita, commanding cruiser forces in the Southwest Pacific, requested analysis from technical specialists. How were Americans achieving such precision? The response from Japanese naval engineers was grounded in conventional understanding. American radar had improved. Fire control computers were faster. Range-finding equipment was more accurate. Gun crews had months of combat experience. All of these factors contributed to incremental improvements in anti-aircraft effectiveness. The analysis concluded that American defensive capabilities were approaching the theoretical maximum achievable with existing technology. The analysis was correct in every detail except the most important one. American defensive capabilities were not approaching the theoretical maximum of existing technology. They had leapfrogged that maximum entirely through technology that Japanese experts had concluded was impossible to manufacture at scale. The proximity fuse represented not an incremental improvement, but a categorical shift in what was achievable in aerial warfare. Every calculation that governed Japanese operational planning was now based on false premises. Yet, because those premises seemed so thoroughly validated by decades of technical understanding, no one questioned them. By summer 1943, American production of proximity fuses had reached 40,000 units per day. The technology that Japanese engineers considered too expensive and complex for mass production was flowing from 110 factories operated by 87 different firms. Sylvania alone employed 10,000 workers, mostly women, producing 1 million vacuum tubes every 2.5 days. This was 2/3 the production rate of the entire pre-war American radio industry, applied to a single component of a single weapons system. The cost per fuse had dropped from $732 in early 1942 to $18 by late 1945. The American industrial machine had done what it always did when properly motivated. It had taken a laboratory curiosity, a device that worked sometimes under ideal conditions, and transformed it into a mass-produced weapon available in quantities that made conservation unnecessary. By late 1944, American commanders could use proximity-fused ammunition without restriction. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated. Defensive fire plans could cover vast areas with overlapping patterns. For Japanese naval aviation, the impact was crushing. By 1944, experienced carrier pilots who had survived Pearl Harbor, the Indian Ocean, Midway, and the Solomons were gone. Not all at once in a single catastrophic battle, but gradually, mission after mission, worn down by defensive fire that seemed impossibly effective. Replacement pilots arrived with minimal training, sometimes less than 100 flight hours total. They faced American task forces whose anti-aircraft defenses had become impenetrable to conventional attack methods. Captain Mitsuo Fuchida, who had led the attack on Pearl Harbor and survived the war, wrote in his post-war memoirs about the psychological impact of facing American ships by 1944. "We knew that attacking American carriers was likely to be our last mission. The defensive fire was so intense, so accurate, that survival seemed more dependent on luck than skill. Our doctrine called for coordinated attacks from multiple INDIT directions to overwhelm defenses. But American ships seemed to track every aircraft simultaneously, detonating shells at precisely calculated distances. It was not merely effective fire. It was fire that seemed to violate the basic principles we understood about anti-aircraft warfare. The violation of basic principles extended beyond tactical effectiveness to strategic sustainability. Japanese carrier aviation, built on a foundation of superbly trained pilots operating advanced aircraft, could not replace losses faster than American defenses inflicted them. Each engagement reduced the pool of experienced aviators. Each replacement pilot was less capable than the veteran lost. Training programs were shortened to meet demand, which further reduced capability. The downward spiral accelerated with each month. By late 1944, Japanese naval leadership faced a crisis that conventional military doctrine could not solve. Attacks by conventional means were resulting in unsustainable casualties. Pilots expressed declining confidence in their ability to penetrate American defenses. Morale was deteriorating as aviators understood they were being sent on missions with minimal chance of success. The mathematics of attrition warfare that had seemed manageable in 1942 had become existential. At current loss rates, Japanese carrier aviation would cease to exist as an effective force within months. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The solution, if it can be called that, emerged from desperation rather than strategic insight. Vice Admiral Takejiro Onishi, commanding 1st Air Fleet in the Philippines, proposed what he called special attack tactics. Rather than attempting conventional bombing or torpedo runs that required surviving defensive fire long enough to aim and release weapons, pilots would deliberately crash their aircraft into American ships. The aircraft itself would become the weapon. A pilot needed minimal skill to point his aircraft at a target and maintain course. Defensive fire might destroy the aircraft, but the pilot's commitment ensured he would not break off the attack. Even if shot down, the flaming wreckage might still reach the target. The tactic was called kamikaze, after the divine wind that had saved Japan from Mongol invasion in the 13th century. What Japanese leadership publicly described as noble self-sacrifice was privately understood as admission of failure. Conventional attacks had become so ineffective that suicide was the only remaining option. The first organized kamikaze attacks launched from the Philippines on October 25, 1944, during the Battle of Leyte Gulf. The results seemed to validate the desperate gamble. Multiple American ships were hit, some were sunk, casualties were significant, but proximity-fused ammunition proved equally effective against kamikaze attacks. The mathematical advantage that made conventional bombing nearly impossible also made suicide attacks vastly more costly. A kamikaze pilot closing on a target presented the ideal scenario for proximity fuses. Predictable course, constant bearing, closing range. Gun directors could track the target continuously. Shells would detonate in the flight path, creating a gauntlet of lethal fragments that few aircraft could penetrate. American naval forces developed sophisticated defensive doctrines specifically for kamikaze attacks. Combat air patrols would engage at maximum distance. Radar picket destroyers positioned far from the main fleet would provide early warning and attrit attacking forces before they reached primary targets. Ships equipped with proximity-fused ammunition would create overlapping fields of fire. 5-inch guns would engage at long range. 40mm and 20mm guns would provide close-in defense. The system worked. Most kamikaze attacks were destroyed before reaching their targets. On May 11, 1945, during the Battle of Okinawa, the destroyers Hadley and Evans, with 4 landing craft supply ships, faced a 90-minute suicide attack by 156 Japanese aircraft. At the end of the engagement, Hadley had knocked down 12 enemy planes. Evans had accounted for 23 before being forced to retire after 4 hits. The small group of American ships, their guns firing proximity-fused ammunition at maximum rates, had survived what should have been overwhelming assault. The Bureau of Naval Personnel's subsequent analysis used one word to describe the role of proximity fuses: indispensable. Japanese naval officers who survived the war consistently reported in post-war interrogations that they had never understood why American anti-aircraft effectiveness had increased so dramatically after early 1943. Most believed Americans had developed superior fire control radar or had integrated aircraft detection with gun directors in ways Japan could not match. Some Japanese engineers speculated about radio-controlled shells, but dismissed the concept as technically impossible given the forces involved in gun launch. The idea that individual shells could carry miniaturized radar systems seemed beyond credible technology. This failure of imagination allowed the proximity fuse to remain operationally secret throughout the war. Despite firing millions of shells, despite the certainty that some would be duds that fell intact into Japanese hands, despite the visible evidence that something fundamental had changed in American defensive capability, Japanese technical officers never grasped what they were facing. The premise that proximity fuzes were impossible to manufacture at scale was so deeply embedded in their understanding of industrial capability that no amount of evidence could dislodge it. The human cost of this failure was substantial. Japanese naval aviation lost over 12,000 aircraft in combat during the war. Documented evidence shows proximity fuses accounted for destroying several hundred of these aircraft directly through anti-aircraft fire. Each aircraft represented not just material loss, but trained aircrew impossible to replace. The death of experienced pilots in 1943 and 44 forced Japan to commit poorly trained replacements who fell victim to American defenses at unsustainable rates. By 1945, Japan resorted to kamikaze tactics, partly because conventional attack methods had proven ineffective against American ships equipped with proximity-fused ammunition. The statistical analysis painted a stark picture. Against kamikaze attacks between October 1944 and January 1945, American 5-inch guns firing conventional ammunition required an average of nearly 500 shells per aircraft destroyed. Guns firing proximity-fused ammunition required less than 70 shells per aircraft destroyed. The efficiency improvement was 700%. For Japanese admirals watching their air groups disintegrate mission after mission, the mathematics were inexplicable. They had been promised that American industrial capacity would take years to mobilize. They had been assured that Japanese technical superiority in torpedoes, optics, and aircraft design would offset American numerical advantages. They had calculated that loss rates sustainable in the war's first year would be sustainable throughout the conflict. Every assumption proved wrong, but the most catastrophic error was underestimating American ability to translate scientific knowledge into industrial production. Admiral Soemu Toyoda, who commanded the combined fleet from May 1944 until war's end, faced the accumulated consequences of these miscalculations. By summer 1945, Japanese naval aviation effectively no longer existed as a strategic force. Training programs had been gutted to provide pilots for kamikaze missions. Fuel shortages grounded remaining aircraft. American air superiority was absolute. When Emperor Hirohito announced Japan's surrender on August 15, 1945, Toyoda was among the senior officers who understood that continued resistance was militarily pointless. The will to fight remained, but the means had been methodically destroyed. In the surrender negotiations and subsequent occupation, American technical teams entered Japan with explicit instructions to assess Japanese understanding of Allied technology. The U.S. Naval Technical Mission to Japan, established on August 14, 1945, sent 655 officers and men to survey Japanese scientific and technological developments. Key Japanese naval personnel and scientists were produced for interview and interrogation. The teams visited laboratories, examined equipment, reviewed documents, and compiled comprehensive reports on Japanese capabilities. In nearly every technical field, American investigators found sophisticated Japanese research. Optical equipment matched German precision. Torpedoes exceeded American capabilities. Submarine designs showed innovative features. Aircraft engines demonstrated advanced metallurgy, but in the field of proximity fuses, Japanese development was essentially non-existent. Limited research had been conducted on photoelectric phases for bombs, using sunlight reflected from targets to trigger detonation. These devices worked only in daylight and malfunctioned if they detected the sun directly. When American investigators asked Japanese engineers about radio proximity fuses, the responses were consistent. Such devices were theoretically possible but practically impossible to manufacture. The acceleration forces were too extreme. The miniaturization required was beyond current manufacturing capability. The cost per unit would be prohibitive. Quality control at scale was unachievable. Even if prototypes could be built, they could never be produced in quantities sufficient for operational use. Japanese engineers had reached these conclusions based on rigorous analysis of known manufacturing capabilities. They were correct about Japanese capabilities. They were catastrophically wrong about American capabilities. The interrogations revealed the depth of Japanese miscalculation. Senior naval officers expressed genuine surprise that Americans had not only developed but mass-produced proximity phases. They had assumed that the increased effectiveness of American anti-aircraft fire resulted from incremental improvements in conventional technology. Radar direction had improved, fire control had gotten faster, gun crews had more experience. These were understandable, predictable developments that fit within Japanese understanding of how technology evolved in wartime. The possibility that Americans had achieved a categorical breakthrough in miniaturization and manufacturing had simply not been considered credible. Commander Takeo Yoshida, who had served on Admiral Yamamoto's staff and survived the war, provided perhaps the most telling insight in his post-war interview. We understood that Americans had superior industrial capacity. We knew they could produce more ships, more aircraft, more ammunition than we could, but we believed the quality of individual weapons systems would remain roughly equivalent. We thought that American doctrine would evolve incrementally, constrained by the same technological limitations that constrained us. The proximity fuse proved that assumption wrong. Americans did not merely produce more, they produced different. They changed the fundamental equations governing aerial warfare. We had no framework to comprehend that kind of innovation at scale. The lack of framework for comprehension extended to the highest levels of Japanese military leadership. Admiral Chuichi Nagumo, who commanded carrier forces at Pearl Harbor and Midway and died at Saipan in July 1944, never understood why his air groups were being systematically destroyed. Admiral Takeo Kurita, who commanded surface forces at Leyte Gulf and survived the war, believed until the post-war interrogations that American anti-aircraft success was due primarily to radar improvements. Admiral Jisaburo Ozawa, who sacrificed his remaining carriers as decoys at Leyte Gulf, thought American defensive doctrine had simply evolved to counter Japanese tactics. None of these officers, all competent professionals with decades of naval experience, grasped that they were facing technology that violated their understanding of what was possible. The proximity fuse represented a type of innovation that Japanese military culture was structurally unprepared to anticipate. Japanese doctrine emphasized perfecting existing systems through rigorous training and incremental improvement. The idea that an enemy might simply invent a new category of weapon, manufacture it by the millions, and deploy it so effectively that all previous calculations became obsolete, this was outside the conceptual framework that governed Japanese strategic thinking. Secretary of the Navy James Forrestal stated after the war that the proximity fuse helped blaze the trail to Japan. He noted that without the protection this device provided to surface ships, the westward advance could not have been so swift, and the cost in men and ships would have been immeasurably greater. Admiral Arleigh Burke, who served as Chief of Staff to Admiral Mark Mitcher commanding fast carrier task forces, recalled that by 1945, all 5-inch ammunition was fitted with proximity fuses, and those fuses knocked down enemy planes by the dozens, preventing ship losses and casualties that would have been enormously larger without this technology. British Prime Minister Winston Churchill noted that proximity fuses made in the United States proved potent against the V-1 rockets that assailed Britain in 1944. The technology that Japanese admirals never imagined possible had become so commonplace that British anti-aircraft batteries along the English Channel were equipped with American proximity-fused ammunition firing from British guns. In the 4 weeks that VT shells were fired from radar-controlled guns against V-1 rockets, success rates climbed from 24% in the first week to 79% by the end. The rockets that had terrorized London were stopped by the same technology that had devastated Japanese naval aviation. The statistical evidence compiled after the war painted a comprehensive picture of technological dominance. Over 22 million proximity fuzzes were manufactured during the war at a total cost of approximately $1 billion in contemporary currency. Production involved 110 factories operated by 87 firms employing tens of thousands of workers. The supply chain required coordination of hundreds of specialized suppliers, delivering components to specifications measured in thousandths of an inch. At peak production, the American electronics industry was manufacturing 70,000 fuses daily, each containing 130 precision components, including 5 miniaturized glass vacuum tubes. This industrial achievement equaled the technical accomplishment. Japanese military planners had assumed that American production would focus on quantity over quality. They expected more ships, more aircraft, more ammunition, but not fundamentally different weapons. The proximity fuse demonstrated that American industry could achieve both: mass production of sophisticated electronics at scales that made the devices economically viable for single-use munitions, quality control sufficient to maintain 90% reliability across millions of units, supply chain coordination that kept assembly lines operating at capacity throughout the war, training programs that enabled workers without advanced education to perform complex technical assembly. These capabilities reflected organizational and industrial structures that Japan could not replicate. American industry had developed mass production techniques in the automotive sector that transferred directly to weapons manufacturing. American universities produced engineers trained in systems integration and quality control. American workers had experience with assembly line manufacturing at scales unknown in Japanese industry. American companies had management structures capable of coordinating complex supply chains across thousands of miles. All of these advantages compounded to create an industrial base that could not merely outproduce but out-innovate Japanese industry. The proximity fuse stands alongside radar and penicillin as one of a handful of technologies that materially affected World War II's outcome. Unlike radar, whose development occurred in multiple countries simultaneously, the proximity fuse resulted from deliberate application of existing knowledge to a specific problem. Dr. Merle Tuve and his team at Section T identified what needed to be done, determined how to accomplish it, and executed a program that achieved operational capability in under 3 years. This focused approach to weapons development became the model for Cold War military research programs. The Manhattan Project developing atomic weapons followed similar organizational patterns. Post-war missile programs adopted the same structure of university laboratories, industrial contractors, and military oversight. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.